I'm pleased to introduce our today's speaker, Professor Boris Zilber from University of Oxford, and you see the title of his talk, A Modal Theory of Modular Curves. Please, Boris, you can proceed.
Yeah, thank you very much for inviting me to speak in your seminar. It is not the first time that I'm speaking in this seminar, but the first time in this new mode. Right. So it's so this work is it's a joint work with Chris Dow, who is much better expert in Shimura varieties and modular curves, and I'm learning on the go. And the whole project is actually a project that comes from logic, from model theory, and so you will see some emphasis that I'm making on logical motivation for mathematical questions and where it leads. Okay, so let me remind you first that what are classical modular curves? It's a modular space for elliptic curves. The base one, which is called which corresponds to n equal to 1, is exactly the modular space for elliptic curves. And then if you also add to the parameters that pick n torsion on the elliptic curve, then you have level n modular curves. And so in terms of upper half plane, so you have on the upper half plane you have a Möbius action, and if you pick a certain subgroup that so gamma 1 would correspond to the whole group SL to Z, and gamma n are modular n subgroups, and so you get you quotient upper half plane as an analytic complex complex manifold. You quotient it by this discrete subgroup, and you have a certain complex manifold, and this complex manifold can be realized as an algebraic curve. So this is an equivalent alternative way of looking at what this is, and then you have also this map that gives you this analytic covering, and when n equal to 1, this map is called J function or J invariant, which gives you a module of an elliptic curve, or the invariant of the elliptic curve. Right. So usually you will see these algebraic curves defined over cyclotomic field of the corresponding degree. But as a matter of fact, you can define this as a curve, as an algebraic curve, not as a specifically level n structure, but as an algebraic curve. You can define it over Q. And the difference between this sort of definition and the definition that requires the presence of roots of unity of order n in your parameters is that in this definition you don't have the action of this group definable. So you have to consider extra parameters, which are essentially this cyclotomic extension of Q. Anyway, so this is, of course, well-known facts. And so this is a setting that I considered. This is all the definitions are over Q. And to give you a better feeling of what it is, so the examples. So the very first curve is just a complex line, and over it, the second level is the very interesting classical the projective line minus 3 points, and then we have many more. So the overall picture is like this. So we have this analytic holomorphic covering maps. So this is actually, this should be seen as a complex manifold, and then you have not exactly a tower, but so the net of modular curves with finite order maps between them, and from the top you have holomorphic covers. Okay, so this is the immediate picture that emerges. But this picture is not that can be extracted from the data given to us. In particular, you can, the important ingredient of this structure is that you also have actions of the respective groups. So on H, in fact, you have this Möbius action of actually of GL2R with positive determinants, but the ones that can be visualized or can be traced in the algebra geometric context is the GL2 plus Q action on the upper half plane. Well, of course, when you trace this action on a finite level, then it is not an action of a group anymore, if it is this general kind of actions. But it is still a proper action by quotients of this group. So this actually does act here, and this is important algebraic structures that that we see in this picture, and of course many more, much more, like well, from algebraic geometry point of view, very important, of course, is that you have Zariski topology here. And so here it is some analytic topology, if you want, analytic structure. And here you have what we in model theory call Zariski structure, which essentially means that you have relations on each of these one-dimensional structures that are given by, well, let's say, polynomial equations. And these polynomial equations are with coefficients over Q. So this is the structure. Now, if you take a pullback of this sort of structure, of this relation, so what are polynomial relations here at this level? So you pull them back here, and you will have analytically given equations and corresponding what we call relations, right? Now, from model theory point of view, we are interested in looking at the what you have seen in the previous slide as structure. Actually, it is what we call multi-sorted structure, because you have so each of these curves is a sort, is an object, is a structure, and the whole thing is a structure that unifies all the sorts with all the arrows between them. So we want to understand this structure as a whole, and our ambitious aim is that give it a description in a way like we give a description to, for example, what is a vector space, what is a field, what is algebraically closed field. So by some collection of axioms in appropriate setting. So the axioms would require to speak about certain relations, certain functions in your structure. So we want a description, or we call it a theory of this structure, but the one that determines the structure uniquely up to isomorphism. So again, if now you forget that this structure is actually made of these complex numbers, or whatever the usual, the standard understanding of what these are, and describe this as an abstract structure with something given here, something given on this, and this arrows being relations. So try to describe it as a up to isomorphism. So of course the question is why would we expect this to be possible? Why this can happen? Well, first of all, the underlying structure in all these cases is, of course, the structure of the field of complex numbers. And for the field of complex numbers, this is a very well known fact that once you say that you are dealing with algebraically closed field of characteristic 0, which you can easily say in a formal language, and you then also add the fact that this is of cardinality continuum, that today we allow ourselves to, we actually fix this assumption everything is of cardinality continuum. Then up to algebraic isomorphism, the field of complex numbers is given uniquely up to isomorphism, right? But this structure is much more complicated. In particular, it has this analytic nature, and so why in this case? So actually, this sort of project, this sort of attempts was started some years ago. And the first example that we considered was this one. So the cover for the case when you have this algebraic torus, complex algebraic torus, the cover would be the complex plane, the whole complex plane, not each. And the covering map is a classical exponentiation. And already in this case, yeah, so in this case, well, I initially proved that it is categorical, but for you to understand that it is not quite trivial, it turned out that my proof had a gap. And we later, 7 years later, we fixed the gap with my then student Martin Bayes, and then now you see this whole work required. So on model theory side, it requires some advanced Shalaz theory of abstract elementary classes. And on the number theory side, it requires well, some standard Kummer theory and well-known Dedekind theory of Galois action on the torsion. So these are the ingredients of this theory. Then we extended this project to the cases where it is still so it is still a cover coming from the complex plane, but then here you have elliptic curves, and in this case, so the model theory component is still the same, and it remains the same throughout. But the number theory side becomes slightly more complicated. So it is now this Kummer-Bashmakov theory of, I think Bashmakov's theorem, it's 1970s maybe. And in place of Dedekind theorem, it is Serre open image theorem on Galois action on torsion of elliptic curves, and this is quite non-trivial theorem. And so extension of this theorem, for example, on abelian varieties is unknown. It's still an open question, and that's why some attempts to carry on this project for abelian varieties turned out well, stuck at this level, and it is only proved conditionally. So this Kummer side, Kummer level theory is known. It is by Kummer, Ribet, by Kenneth Ribet and Michael Larsen, and for the open image theorem is expected, but it's not known. Is conjectured, but it is not known. Right. And then the next level we tried is the so all the previous ones were abelian examples, abelian algebraic geometry. And this is a hyperbolic, or the first unabelian case. It is when you consider it covered by the upper half plane. And this was part of this project was carried out. And but it is also only partial result, quite similar to this one, because they didn't know the analog of Serre open image theorem. In this case, you also need something. Namely, you need to understand the action of the Galois group on CM points. And if you don't understand it, then you pay a price that your field of definition has to be quite large. So this field, for example, it extends all the cyclotomic fields. It is so it is so we want this to be a number field. In fact, the aim of what I'm reporting about today was to do it over Q, right? Okay, so that's the situation on before this project was started. Now, what sort of axioms to expect? So what is a natural definition? You see, I use this word natural. So what does it mean that natural axioms or natural descriptions? And so the description actually splits into three relatively simple parts. Well, the number one, so you have here some algebraic curves, or in more general case, it would be algebraic varieties covered by this analytic object. And the first thing you do, you describe what are these things on the right. So of course, you say that you are dealing here with algebraically closed field of characteristic 0. And then you give equations or whatever it is, in whatever terms this is given, of these varieties, right? So these are varieties that are given by certain equations over, well, these are C points of, well, you can say schemes over this number field K, right? So this is the first part of your description. The second part, and this is really where you have to turn on some sort of model theory thinking in model theory terms. So actually here on this part there is some remarkable, simple but important structure. So, for example, in case when this is exponentiation, you immediately depict here the linear structure. So this is a complex plane you would be dealing with. And what you would be talking about at this stage is that this is there is the structure of a module here, and this is essentially it. And this sort of structures, there is quite general classification theory about three types of structures, that some trichotomy. so this sort of structures would be called locally modular structures. I will say a bit more about. So essentially, the locally modular structures are of two types: locally modular structures of linear type, and locally modular structures of trivial type. So more of this later. So once you have identified this, well, combinatorial algebraic structure here, you then, in this natural description, you then tell how this function relates this, for example, linear relations here with whatever relations, appropriate relations are here. So when you when you deal with exponentiation, so you would say that additive relation here goes into multiplicative relations here. So in fact, you say that exponentiation is a homomorphism, right? So it is a covering homomorphism. But you can look at this statement as the statement as a functional equation. So it describes you the properties of this function Fn. So in it's very similar situation in the abelian varieties case. And when we talk about we start thinking about hyperbolic cases, then what we will see here is what in theory of Shimura varieties is called special relations or special subsets. Special subvarieties, and so this functional relations, they say that certain algebraic relations here correspond to special subvarieties inside here. So this is what you say in your axioms, and you would expect that these axioms would determine the structure uniquely up to isomorphism. So that's what is interesting. Okay. Yeah. So this is proved to be quite general pattern, and that's also is telling something. In fact, it is kind of saying that this pure structure here, this locally modular structure here, is some sort of invariant of what we see in algebraic geometry here, and this invariant is actually of topological nature because this is a topological cover, and yeah, topological here is quite important. Right. So what I said a few words about this abelian case, this hyperbolic case that we are dealing here. So our problem is to understand what is this structures that I classified it, or we expect it to be locally modular of trivial type, whatever it means. But now this is our main problem to say concretely what is it here, this structure, right? Okay, according to this very general principle of the classification theory, model theory, classification theory, so in abelian case, it would be locally modular of linear type. And in hyperbolic case, it must be locally modular of trivial type. And what we know in advance, that locally modular of trivial type is essentially, well, essentially needs a lot of explaining here, but let me just jump over it. So it is essentially a G set. So G would be some group that you have to describe, and this group acts on H, and we immediately start guessing what this group G should be. So this group acts on G, but also, of course, this action doesn't have to be free. So you will have some fixed points, and possible also relations between these fixed points that could again be dependent on the structure of G. So it is not completely trivial just by saying that it is this group G. And then you see, important part of understanding all this, this multi-layer, multi-sorted structure that I talked about is to understand this homogenized version of this cover. Homogenized in what way? Well, we actually, of course, we can approach this H by taking a higher and higher level of these modular curves. And when we take a projective limit, we get, so this is actually the definition, we get this object. And this object is very homogeneous in the sense that it has all the automorphisms as these curves have. So the automorphisms of these curves can be lifted to automorphisms of this structure. And this obviously sits inside. So you can, instead of going straight down here, you can actually find this H inside H tilde and then use the map down. Just by following this definition, right? So so this is very homogeneous object, a lot of automorphisms, and this is not. This is when you apply automorphism to this, so you will move this H inside it, and it was a question raised probably already by Shimura and then later formalized by Langlands. So there is a conjecture by Langlands of 1974 who essentially asked how to describe what happens with H under the action of automorphisms. And this generated a lot of theory, which is very relevant to this problem that I'm now reporting on. Right. So the question is to understand this as a structure and to understand its automorphisms. So I'm formulating it here, and in particular, you should also understand, of course, so what previously was the action of G. Well, in our case, this G is of course GL2Q, with positive determinants. So so what is a projective limit of this? Well, this is actually not this is well defined, of course, and this is not so this is not right. It is not group structure, of course, by this definition, but it is something you need to understand. In fact, it becomes a group after some right definition. Okay. And so this then become, in order to understand this, we come to what in the theory of Shimura varieties is called canonical models for Shimura varieties. And in this case, it is canonical models for Shimura curves, because we are dealing just with the case of modular curves, or which is the same as Shimura curves. Right, and this whole theory is related to working over the ring of Adels, and in fact, more specifically, we can consider the ring, the subring of finite Adels. So it means that we don't consider the component that corresponds to Archimedean valuations. Okay, so these are finite Adels, and then for the case of Shimura curves, so we take this complex manifold, which is the upper half plane together with the lower half plane. You take a direct product, the abstract direct product with this guy, and you consider this double cosets. So here you can factor by open compact subgroups of this group on this side, and on the left you see you have an action of GL2Q on X, right? Because GL2Q acts on H together with the low half plane, right? So it is well defined, the action of this here, and you also have action of this. It is actually a subgroup of this guy. So you have it makes sense to quotient by this subgroup, and this one is only applicable to this side. Okay, so this set-wise, it is just the set of double cosets, right? But it also can be considered a scheme. Well, in fact, is some sort of complex manifold, because here you have a complex manifold, and then what happens in this whole construction is that you kind of take many copies of this by multiplying it by this, and then glue them together in this quite complicated process, and so you get this. This is also sometimes called, in the most general case, it is called Mumford manifold. But this can be understood as the complex scheme, as C scheme, and you have automorphic forms on this in very general setting. But when you factor after factoring by this open compact subgroup, so this actually becomes a complex algebraic curve. but we should be aware that here what you have is so this is complex algebraic curve, but generally it is a reducible curve. It splits into finitely many irreducible components, Zariski irreducible components. Right. So, but for K here, sometimes it makes sense to take this K to be compact, but not necessarily open. So, for example, K to be trivial equal to 1, just the identity. It also makes sense. And in this case, so for example, when K is equal to 1, this can be seen as the projective limit of these algebraic curves that I've just described. And what is interesting that what the reusable components here in the limit, they become some irreducible components here, and you have continuum many of those. And these irreducible components are actually indexed by z hat star, which is isomorphic to the Galois group of the full cyclotomic field. Okay. Now it turns out that in this way you can describe this H tilde. So our homogenized version of the upper half plane. And H tilde is simply when you take this guy and you factor it by this diagonal group. So this is not difficult to check, and so our questions become very close to just the theory of canonical models that is well developed now because of there is a good 150 pages paper by James Milne, which describes, which gives all the details of this theory. But many people, of course, worked on this, starting from Shimura, and Borovoy gave his own solution to this Langland's problem. And Milne and she also there is somewhat different setting of this solution. Okay, and so in this case, yeah, once you identify the H tilde in this form, you also can identify what these analytic maps, how you represent them going from this H tilde in this form onto this, and you can now identify these things with the algebraic curves that come from this theory. So namely, you take a quotient, so your k in this case, right? So what that's this k that you have here, it has this quite a concrete form. So this group is just a subgroup of the group of finite adels, or finite adel, right? And natural here is to take this pure structure that would lead us to H pure. to be just GL set on this. So you have our S as in the previous slide, and you have an action of this group on this S, and that's it. That in this setting is this very simple structure that we need to understand. Now, if you factor this structure, you go down to algebraic curves, and so on algebraic curves, you have also then certain structure. And this structure is essentially the structure of special sets with a little bit more on it. Now, in contrast with this pure structure, I also use this terminology that there is a full structure here, which would include all this Zariski structure. So the polynomial relations, whatever they are, the rational functions that are defined on these algebraic curves, they all would be part of this structure. And the structure of the field, of course, would be visible here. Right. And now I'm going to through some technical definitions which are standard. So what are CM points? So on these modular curves, if you think of them as being modular spaces for elliptic curves, then those which correspond to elliptic curves with complex multiplication, so this very special elliptic curves, so these are called CM points. Now, an alternative definition, here you will see two alternative definitions. You can get all the CM points by going through this procedure. You go to the cover, which means this tau is a point on the upper half plane, right? But you pick the point on the upper half plane, which is quadratic, which means that it has this form. This is obviously purely imaginary. And the R and T are rational numbers. So you have this quadratic point. So if you apply your J function to a quadratic point, then you get a point on the modular curve, which is exactly a CM point. And that's, you can take this for definition of CM point in this analytic setting. And one more equivalent form of this definition, if you think in the terms of canonical models, is if you see this as such a thing, so it is a quotient by certain subgroup, right? And then you take this coset to be the representative of the coset, should be a fixed point of some element of GL2, adelic GL2. So these are three equivalent definitions. And now I remind you that CM points are algebraic. And so you can act on them by Galois action. So these are algebraic points. Right. So now we concentrate on trying to understand what is the structure that this. So you take a pure structure, you take CM points inside it, so you get substructure. So it is, you restrict your structure to CM points only. But the relations that you want to see in this case are only those pure relations, and that's another version. You want to see full relations, and it is clear that if you apply automorphisms of this structure with full relations, so you have less automorphisms than in this case, and so you have this embedding, and so but by the nature of this construction, because CM points are all everything that you have on algebraic curves, you see this actually all comes from algebraic curves. And whatever relations you have on these algebraic curves, they would be expressed in terms of algebraic geometry, and so you, in fact, when you act on this biautomorphism of the structure, it is the same as Galois action. And now we have two main algebraic results. So the first result is that we have a full description of this automorphism group. Yeah, so you see this equality is already here for us, but this can be bigger, maybe much bigger, if relations that are visible here, if we have more relations here than we have relations here. But in fact, it is the same. So whatever relations are between CM points, they are already picked by this pure structure. That's the meaning of this theorem. So so this is quite important, that so this pure structure, what we classify it as a locally modular structure. So the Galois group is the same. So the relations between the CM points are essentially of locally modular type. That's the meaning. Now we can compare it with Serre open image theorem. So what Serre open image theorem says is that if you consider torsion points on elliptic curves, right? So instead of CM points, you will have to consider torsion points on a fixed elliptic curve. Right. So Serre theorem says that what the Galois group picks here is that the only relations between them are linear relations. So only the group relation, well, essentially, well, it is almost, there is a formulation in there. Okay, and so you will have equality between this and automorphism group of a certain linear structure, namely this group structure. So this is equality between certain linear structure in Serre case, equality between this automorphism group of the linear structure and the Galois group on acting on the special points of elliptic curves, right? So this is analog of this, and you can use this plus a lot of details that is known about this theory, this rich theory of complex multiplication, and Artin symbol. It's all involved in this analysis. And you can work out exactly of what this group is. So it is extension of order 2 of a huge torus. So, in fact, you have to consider well, GL2, the Cartesian power of GL2, in fact, and inside this Cartesian power, you have a Cartesian power, well, Cartesian product of infinitely many tori with adelic points on the tori. So it is a huge abelian group, and then it is just a action of complex multiplication on this abelian group, or action on a group of order 2 on this. That's a full description of this. Right. So I already said that it all uses the many facts that you can extract from literature. Now, concerning this theorem B, which gives you exact form of this Galois group, Milne, yeah, actually I asked Milne, and he pointed me to this paper, and that's what he says. He says that it should be something like this, right? So this is all that there is in this paper, in his paper. And when he says in this case, he means that in the case of Shimura curves, in the case of modular curves, this group can be worked out. In more general case, there is no something, whatever precise you can say. So this this means that this theorem is some sort of predicted, but not nothing concrete proved or published here. But we see this is in fact this theorem follows from theorem A. Theorem B follows from theorem A and well-known facts, but not the other way around. Okay, and that's the difference. And because we can have now such a good picture of this the canonical models, we can the pure part of these canonical models, we can now describe the pure part of the homogenized upper half plane and the upper half plane itself. So it can be described in explicit terms. And that's what we need to formulate our axioms. So now we can formulate the main theorem. Actually, this is for us the aim of our project. And so we prove that we give a natural infinitary description. So infinitary, it means that in certain language that we call L omega 1 omega language. And it gives an axiomatization of this object such that if you have any other structure of this same form that satisfies the same axioms, the same description, right? So this is another structure. Then, and you know that the field here is abstractly the same as a field here, right? So it the isomorphic as abstract fields. Then you can pick you can pick a special well, appropriate isomorphism between these two fields that of course will give you then also isomorphism between it's a kind of Galois isomorphism between the curves. And it would agree with uniquely defined isomorphism on the top, right, on the analytic part. And so that's the meaning of this theorem, right? And as I said, it is a main theorem. Now, if you still remember, in similar circumstance, in similar previous examples, we said that to prove this categoricity statement, you have to use a lot of this number theory kind of information. And of course, in this case, the proof relies on this theorem. Actually, sorry, I should have said, no, it is theorem A here. Sorry. Yeah, so this is this theorem. This is theorem that is key. Right, so analog of Serre theorem, as I said. Okay, so and plus to this, the usual Serre theorem, open image theorem, which is hidden in the use of the early result. We also have to use the early result of Chris Dow and Adam Harris. Right. So when I say relies heavily, so in all those works, in all these examples, this relies heavily actually means that the categoricity theorem implies this theorem A. So so you see this model theory formulation, if successful, then it would give you this number theoretic and algebra geometric information. But of course, what I'm saying here is to prove it, you need certain kind of algebra geometric number theoretic data. And in this case, yeah, what I explained here, you use all this rich theory that I went through with you. Okay, so this is, yeah, that's, this is the last slide. Thank you very much. Oh, I'm sorry, I went over my time.
Yeah, thank you. Let's thank the speaker. Questions to the speaker, comments, remarks? I just wanted to ask you about the sentence you said that you wanted to get some explicit form of this H tilde. In which sense it is explicit? So do you get some polynomial equations, some systems, or what?
Well, that's why I use these terms, this locally modular structure of linear type or of trivial type. So it means that well, in this case, you present, you say that in your description, this is important to explain how GL2 acts on the upper half plane. But just to tell you that it is not complete triviality. It is, you see, GL2 will have its own automorphisms as well. In this adelic version, it has quite a few automorphisms. And you need to understand these automorphisms as well. Plus to this, when I presented this, the structure of CM points, in fact, so the structure of CM points is certainly an important part of this pure structure on H. And on H, you would have the CM points are essentially the quadratic points, imaginary quadratic points. And it turns out, so you have to say what are exactly relations between quadratic points that are visible in this theory. You cannot just say that the quadratic points generate the field and you have addition and multiplication or whatever. By the way, they don't generate the field because it is only the upper half plane that you have here, and so this is and in fact there is a very delicate relation between these quadratic points that without which you cannot have a correct theory. So your theorem fails. Your categoricity theorem fails if you haven't identified properly the relation between the CM points, namely between these points, and their adelic realizations. Adelic realization is more appropriate here. So that's what I'm talking about.
Okay, thank you. More questions?
Yeah, I have a question. Can you, as a result, categorify the real cycles, the real Heegner points, not points, but cycles?
Can you say this a bit more loud?
Can you, so you categorify and you use CM points, but there are also similar cycles, Heegner cycles. Can you, as a result, somehow?
Well, I'm not sure. It is no, but this yeah, it you mean the group of cycles or what?
Yeah. Yes, groups.
Yeah, that's a very good question. In fact, I sort of tried to say that the structure on what I call this H pure, it is there is a lot of information hidden in it, and this looks like the most complete algebra topological information that you can extract from modular curves in the complex setting. So it looks like it is some complete topological invariant. Maybe even you can compare it with motifs. But you have to decode it. You have to So, by the way, I didn't mention that the other aspect of this whole theory, so I avoided it. It is the connection with transcendental properties of this same functions, and then where you go into the period period conjecture, and again you have all this motivic information. So that's why it is important that you see, understanding this this structure, or more importantly this structure. So it looks to us as having hidden So you can extract all the topological algebra topological invariants.
More questions?
Thank you.
So if not, let's thank the speaker again.
Thank you.
I stop recording and